So I'm sure we can see my screen and uh, I'll start. So please, can we see my screen? Please let me know if you can see my screen. Okay, I assume we can. So we want to talk about correlation and regression in statistics. Correlation and regression. Please, can you see my screen and can you hear me? Okay, I assume that's say.
Yes, yes, we can.
Okay, thank you very much. Now, we want to talk about correlation and regression in statistics. Now, since when we started statistics, we talked about, I could remember the first section, we talked about introduction to statistics, how statistics help us, to discover things that are hidden in terms of, knowing what the data type is all about, in terms of qualitative and quantitative. From there, we begin to see something called measure of central tendency and measure of dispersion. And I'm sure our other tutors who have spoken about probability, spoken about visualizations, and talk about using visualizations to check up, to look at your data, to see outliers and some other stuffs. And also, this is supposed to be the last class, actually, but due to some reasons, it's going to be second to the last class. Last class is going to be happening on Monday, where we'll be talking about ANOVAs and some T-square statistics, talking about T tests and other stuffs like that. Now, today we're looking at correlation and regression. What is correlation? So we say correlation is a statistical measure that express the extent to which two variables are what linearly related. Correlation, a statistical measure that does what? That express the extent to which two variables are linearly related. What are the key points we're supposed to look at in correlation? So some of the key points is it measures both the strength and direction of a relationship. It does not distinguish between dependent and independent variable. And it's commonly used in data analysis to understand the relationship between what? Variable. So this is not saying, you're not saying that it wants to differentiate. No, it only gives you or show you the relationship between two variables. And when it show you those relationship between the two variables, it's not minding whether it is dependent or it is independent. So correlation is just just like I've said, a statistical measure that express the extent to which two variables are what linearly related. Now, correlation. So when we talk about correlation, we said is the measure is actually best used in variables that demonstrate the linear relationship between each other. So the fit of the data can be visually represented in a scatter plot. So as you can see from the diagram I have here, I have a scatter plot which is showing me a model and an observation. So using a scatter plot, we can generally assess the relationship between the variables and determine whether they are correlated or not. So when you're talking about the scatter plots, I could still remember, like I said, I'm sure the other two have spoken about, some visualization. So a scatter plot is more like a diagram. Talking about the scatter diagram, that is more for visualizing relationship between two or more variables, between two or more what variables. So yeah, using the scatter plots, we can generally assess the relationship between the variables and determine whether they are correlated or not. From this diagram, you begin to see that there are actually what? How many variables there? You see that we have like four, which is the red, blue, the green, and the yellow. And in the way we are looking at it, we are seeing them that they are going up, that they are increasing. So if you look at that of the blue variable, you are saying that you see those color. So those colors are just used to give more meaning to it. So in terms of what we're looking at the models and the observation. So now you see that there are some of these variables are closer to the line, and as they are increasing, they are what? They are moving upward. So as one particular variable is increasing, the other variable is what? Is increasing too, in terms of the model and the what? Observation. So for example, now let's not look at this diagram and start giving what we don't really understand. Let's get to understand it more. Person correlation coefficient. So how do we get to find all this correlation in terms of putting it in this diagram, we need to calculate it. So where we have this, we have literally some other correlation that we can use in terms of Spearman ranking. We have Spearman ranking, yeah, but aside Spearman ranking, we also have Kendall correlation coefficient too. So, but I tend to want to talk about Pearson correlation coefficient because it's quite um the most popular one that I know that people use. And then sometimes it depends on what you want to use them to, find the correlation you want to find. So when you're talking about Pearson correlation coefficient, I've just mentioned that we have three correlation coefficients in terms of Pearson correlation coefficient, Spearman-Rankine correlation coefficient, and Kendall correlation coefficient. So when you're talking about Pearson correlation, you are talking about you using that correlation as a form of finding an inference. So it's more like a distribution of data that is required for what? For inference. So we are saying Pearson correlation. How do you get to represent it? We represent it by this symbol R, and it ranges from -1 to +1. It ranges from what? -1 to +1. Sorry, let me quickly accept. So it ranges from -1 to +1. So now we have the formula for this Pearson correlation. The formula is summation open bracket x minus x bar. From what we started when we started learning coefficient statistics, we already on. I'm sure we already know what x bar is all about. We're talking about mean. So from the formula now, you have the summation of open. So you can see the brackets are two, which means the x minus x bar, y minus y bar, they are inside one bracket as the numerator. So the sum of those two divided by the square root of the summation of x minus x bar all square times summation of y minus y bar all square in bracket as the denominators. Guess what? The x and y are the what? The variables. The bar x and the bar y are what? The means of x and y respectively. From what we have known, we know. Please let's make sure we mute our mic. So we know that when we are talking about mean,
I
we have
want
it
to
to be
know. Yeah.
we have it to be um, summation x. When you're talking about x mean, we have it to be known as summation fx over summation f in terms of when you have a frequency and you have the particular value. But when you're talking about the way we are playing from normal sample, we're saying summation x over what? Over n. Summation x over what? Over n. So now you have that is the total sum of the observation. You have like 1 to 5. You sum 1, 2, 3, 4, 5. Divide by what? 5, because we have how many numbers there? 5. So that's you finding the mean. Summation of what? Those numbers over what? The number of observation, which is 5. I just give an example. So when you're talking about Pearson correlation coefficient, this is the formula you get to use. And know what? It ranges from what? -1 to +1. And your x and y are your what? Your variables. And the bar x, bar y are the means of the x and y respectively. Now let's talk about the interpretation. So when your r is equals to 1, it is what? Perfect positive correlation. That is, there's a positive correlation between them. When your r is -1, you say it is what? Perfect negative correlation. But then we can always have them in ranges, and we are going to look at that as we go on. We will look at that as we go on. Now we have r equals to what? 0, which means that there is no linear correlation. Which means that there's what? There is no linear correlation. Now, it's time for us to understand that when we are trying to solve some of this particular what we are talking about here, we are trying to solve it, and we are trying to find a correlation between something. Then we get to understand that when we find our answer, we need to know what we are trying to talk about. Even that's why when we started, we spoke about scatter diagram, how it gets to help us. We're talking about scatter plots, how it gets to help us in order for us to see. So sometimes when we see a particular chart, now it's easy for us to know whether it is positively there's a positive correlation with it, or there's a negative correlation, or the what? No correlation. So when a chart is now, let's go back to this particular correlation diagram. So you could see that these things are going what? Upward. The data point you are seeing there, these colors you are seeing, they are going what? Upward. They are increasing. So when you have a data like this, showing in a scatter plot like this, going upward, it means it's what? It is There's a positive correlation between the model and the observation we are having. If these things were going downward, they won't go upward like this, they'll go down. So you will see them that they are coming down, not in this direction. So if you look at this diagram I'm having here now, You can see these things are what going up, and it means that as the model is doing what, as it's increasing, the observation is doing what, is increasing too. So you can see, and they are what, getting closer to this line, which means they are close to each other. Now if it was negative, these values will be coming like this. I'm sure we can see my arrow showing that this, how this thing will look like. If it is positive, if it is what, negative, strong negative relation, you see that the line will be drawn, will be drawn like this. They're coming like this, and you see that there will be, you'll be able to see that they are coming downward like this. You see them coming downward. So from this particular place where my arrow is, this is how the line too will go downward, and this point with it would also follow downward. So that shows that what, it's a negative relation, there's a negative correlation. But when you are seeing that this thing are just scattered anyhow, they're just scattered anyhow, you're just seeing this one here, 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 we will see that that shows us that there's no what, there's no correlation, because there's no evidence of correlation in it. But as you can see this line now, if you could remember, there was one time I was talking about outliers. When I say outliers, you just see them, they're just far away from every other person. So you look at this particular blue dot now, you see them, they are close to each other. But see this guy here, this one just fly up. This can be used, or this can be assumed as an outlier, because it's quite not closer to these people here in terms of what we are saying. Now, so if you look at this now, they are what, is a, this is a positive what, correlation. Back to this slide. So now you are saying that when you have r equals to 1, when you have solved, you have your data, you have solved it, and you now see that r equals 1, it is perfect what, positive correlation. And when you have minus 1, it is what, perfect negative what, correlation. And when r equals 0, you have it what, no linear correlation. Work with me. Now, when you're interpreting correlation strength and direction, correlation strength and direction, just what I just spoke about with that diagram that I showed. Now, we're able to know that when something is positively correlated, you say when we have a positive correlation, as one variable does what, increases, the other tends to what, increase. As one variable increases, the other tends to what, increase. Let me give you an example. Now, you have someone working at a particular company, and the person is being paid per hour. Now you get to feel like, oh, because this person is working per hour and this person gets to work overtime, so everybody gets to work probably like 12 hours a day, but this person wants to work what, 16 hours a day, and at the end of the day somebody's having the same kind of work, the same level, is having $500 per day, and the other person working 16 hours per day is getting what, $800. At that meaning, you can say that, oh, because this person is working more hours than the other people, that's why he's getting more money than the other people. In this way, you start to look at it. Is this correlating? Is this, you know, causation? We're going somewhere. But then we can use that example to understand what I'm trying to say. As one variable is doing what, is increasing, and the other will tend to what, increase. Guess what? Negative correlation. As one variable increases, the other tends to what? Decrease. So when one is increasing, the other ones will be what? Decreasing. That's what we talk about, negative correlation. And we're talking about strength. So when you have 0 to 0.3, you call it a what? A weak correlation. Because all these things we are going to, like I said in our assignment, let's get there. So strength, you have 0 to 0.3, which is what? Weak correlation. You have 0.3 to what? 7, 0.7, which is what? Moderate correlation. And you have what? 0.7 to what? 1.0, which is what? Strong correlation. Which is what? Strong correlation. So when you have an example of, okay, the r after you solved, you had it to be what, 0.8, you can call it to be what, strong positive what, correlation, strong what, positive correlation. But when you're having it to be what, negative, it is what, moderate negative correlation. Moderate negative correlation. So this is us trying to understand how we can interpret correlation strength and what, direction. Correlation strength and what, direction. Let's move on. Let's look at this example now. John is an investor, so his portfolio primarily tracks the performance of S&P 500, and John wants to add the stock of Apple to its portfolio. So before adding Apple to his portfolio, he wants to assess the correlation between the stock and what, and the S&P 500, to ensure that adding this stock won't increase the risk system, the increase the systematic risk of his portfolio. To find the coefficient, John gathers the following prices for the last 5 years. I go for the example again. He wants to assess the correlation between the stock and what's that stock? Apple. So he wants to get the correlation between the stock and S5 and P500 to ensure that adding the stock would increase the systematic risk of his what? Portfolio. So to find that coefficient, John had to go and gather the following prices of the for the last 5 years. Now look at the prices. We have the data here. So he went to check for S&P 500 in 2013. This is what he had. For Apple, that's what they have. 2014, same value. You see the values like that. 2015, 2016, 2017. Now, Pearson correlation. What's the formula? I gave us while we were talking about the symbols and the rest, and it's also here too, which is what summation x1 minus x by x. We represent this xi to to just let you know that this is your variable, the main variable. This x bar is your what? This by x is your mean of x. Now in this form, you have S and P to be 500 to be x, a, and you have Apple to be what? To be y. So now what do we need to do now? This is xi minus what? By x. Close the bracket. Y minus what? Y bar y over what? The square root of the summation of xi minus bar x all square summation of what? Yi minus bar y all square. So now we need to use this formula above so that John can determine the what? The correlation between the prices of what? 5 and P500 index and Apple what? Apple 2. Now, work with me. The first thing we need to do now, if you look at this, we have mean here of x and we have mean of what? Y. We need to calculate them. We need to calculate them. And I've told us that S&P 500 is our X in this place. Apple is our what? Is our Y. Now, let's go. So now when we find the mean, you can see down here, the mean of S&P 500 is what? 2044 point what? 83. And you see that the mean for Apple is what? 108 point what? 89. So what do we say here? We said first the John calculate the average prices of each security for the given period. So now after he has gathered those five letters, 2023, 20, so he found the mean because he wants to use the formula. So now we've calculated the mean. Now let's move on. What do we do? After calculating the average price, we can find other values. This is a summary of the calculation given in this table below. Now look at this table below. In this place, in this place, we're having S&P 500. You can see here, I represent it as X, but that's not an issue. I was saying X and Y. This is X, this is Y. But let's go somewhere now. You see, now this is the value we got. You could remember where we have what? The mean of S&P 500 and Apple, where we have it here. Now let's get to our formula. Can you see now we need to find what? Xi minus mean x by x. So it means that we need to start subtracting S&P 500 from what? From the mean. Don't forget, what's the mean of S&P 500? 2044.83 0.83. Now what do we do here? The mean is this is mean, right? This place here. Now when we have the mean to be in this place, now we get to do what? We get to now subtract this one from the mean. So this guy, this particular value now from this mean will give you what? Minus 353.08. Now 197.80 minus this mean will give you what? Minus 7.03. 1884.09 from this mean will give you what? Minus 160.74. 2151.13 minus 2044 2044 point what 83 will give you what 10.30. 2519.36 will give you what 2044 point minus this will give you what 474 point what 53. And remember that anytime you have done all this subtraction, when you get their sum, it will give you zero. That's why you're seeing me putting just sum. That's why this you see these sums here. Now the same thing for Apple, we do it. So now let's get back to that formula. Now this xi minus bar x is what we just did here, that is represented as what? As a here. So we've gotten a here. We have it here. Now B is Apple, that is 68.96 minus 108.89 will give you minus 39.93. 100 plus 11 minus minus this mean will give you what? 87.78. 109.806 minus this mean will give you this, yeah, when you have 112.18 minus 108.89 will give you this. Then when you have 154.12 minus 108 point, so you are subtracting this thing one after the other from the mean to get this. Now this yi minus bar y is what is represented as what? B here. So it's what is represented as B here. So now this is now represented as B. Now we need to now find what? Their products, which is what we have here. Now the product is what? Xi minus bar x in brackets times yi minus bar y in what? In brackets. So we need to get that before we can now get their summation. So now you will now see that we have minus 3 this my times minus 9, you have it to be positive because minus times minus will give you what? Positive. 353.08 times 39.93 will give you this 14,096 point what? 91. Same for this 67.03 times this will give you this 160.74 times 0.17 will give you this times this will give you this times this will give you what? This. Now we have been able to find what? These products. Now the summation of this product is what we have as what? 36,472 point what? 40, which is the value that will be on top here because we have been able to solve for this one on top here. Now this one you are seeing here, this summation xi minus bar x close bracket open bracket yi minus what? Bar y close bracket. We have been able to find that value, which is what we have here. Now, a square is what? This one down here, which is what? Xi minus by x square. So we have it here. This is what we are trying to look for, which is square of this. When you square this, obviously minus times minus will give you what? A plus. So that's why you're seeing that the square of minus 353.08 will give you what? 124,662 point what? 66. Same thing for this 67.0, we square it, we have it here. This we square it, we have this one here. This we square it, we have this here. This we square, we have it here. We do for B2, we square it, we have the answer here. We do for this, we square, we have the answer here. We do for this, we square, we have the answer here. We do for this, we have. So now we've been able to do what? Find each parameters down there. So now for a square, this is the sum, we have it there. This then for b square, you see it here too. Now let's move back. So now we have them here. Now imputing all this that we've gotten, this is going to be in our numerator, this is going to be denominator. They will they multiply themselves and we will find the square root. Now see them here. Can you see it here now? So using the obtained number, John can now calculate the what? The coefficient, which is what? 36,000, 272.40 divided by the square root of 391,474.35 times 3728 point what? 10. When you find this now, you are going to have your coefficient to be what? 0.95. And I'm sure with what we've been able to see from while we started, 0.95 is telling you that that thing is what? Also, it's close to 1, which is what? Positively what? Strong. It is strong. The relationship is what? Strongly positive. That's the correlation. So the coefficient indicates that the S&P 500 and Apple price have a was positive correlation. This means that their respective prices tend to move in the what? In the same direction. So therefore, adding Apple to his portfolio will increase what? Will increase his systematic risks because they tend to what? They are correlated, so they will obviously what? Move what? In the same direction. As one increases, the other will do what? Increases from our knowledge of what? Positive correlation. That's just you trying to get correlation between what? Two values and two variables. But you remember, correlation is not going to, it doesn't care whether you are trying to show a relationship between a dependent and undependent. It does not mind. All is all about is to show the relationship between two variables. That's what he wants to know. It's not minding whether this one is dependent or independent. And that's when that guy called regression gets to come in to help us, make more sense in terms of this is what we want to use our dependent, this is what we want to use as our what? As independent. Work with me. Correlation versus causation. So when you're talking about correlation, you say correlation, we've been able to understand what the definition of correlation is. Then when we talk about causation, causation is just saying an event that happened based on one event. But a key principle is that correlation does not imply causation. But we can say causation implies what? Correlation, but not vice versa. What do you mean by causation? Causation is saying because of this stuff that happened, that's why this other one happened. So, for example, look at this example we have here. Ice cream sales and crime rates both increase in summer. Yes, when we're in the summer period, you get to get ice cream sales to be what? To increase because that time we have sun and everybody wants to like chill out with ice cream to just get to just get chilled, that kind of thing. And as that period too, you get to have crime rate to increase because you know one way or the other, crime rate increase in that summer. So but then the correlation between them is okay, yeah, positive because we perform correlation, but does not mean because ice cream sale is happening in the summer is why crime rate is happening too. It's not because of the ice cream sale. So in correlation, we have positive. Causation, no, but they are both influenced by what? Temperature. They're both influenced by temperature, but doesn't mean because of the ice cream sale, that's why we have crime rate to do what? To increase. But in terms of you trying to find a correlation between them, yeah, you get it to be what? Positive. Now look at the second example. The number of firefighters and extent of fire damages. So when you find the correlation, you find it to be what? To be positive. But causation, no. You can't say because of the number of firefighters we have, that's why the fire damages is so big, is massive. No, nah, no. Because that's what causation is all about. That's what causation is saying. So more firefighters respond to larger fires. Yes, we can say that. But you're not saying because we have larger, we have firefighters, so much. That's why we're having extent, but they are correlating, but doesn't mean that is what causes it. Because we have so many firefighters around now, that's why the fire damage is so spread out. No. So it is very important that you do what? You avoid drawing false conclusions from what? Correlational data. You avoid doing what? Drawing false conclusion from correlational data. Now, we've been able to speak about correlation and get to see why we need to understand that correlation does not do what? Does not imply causation. Work with me. Regression analysis. Regression analysis. So when you're talking about regression analysis, what do we mean? What are we trying to talk about? So we say regression analysis is the statistical method used in finance, investing, and other disciplines that attempt to determine the strength and the character of the relationship between what? A dependent variable and one or more dependent variable. So we could have said a dependent variable and an independent variable, but guess what? Correlation regression is just not, it's not just about linear. We have other type of correlation, we have other type of regression analysis. Sorry, regression analysis. So for example, now from our chart here, it still says the definition of what I've just said. You can see that we have a chart showing that, oh, this is the model. This is literally regression model that we use for predicting. So we tend to use this regression to do what? To determine the strengths. The strengths. So I can remember when I was in studying regression, and like most time regression is just to is to help you find the differences and relationship. Sometimes you to find that difference and relationship. So if you look at it now, you said in this diagram, you said definition we just gave, which is between what? One dependent variable, usually denoted by what? Y. Y is depending on X. The dependent variable, which is usually denoted by what? Y. And a series of other variables known as what? Independent variables. And this, we are talking about independent variables, they are denoted as what? As X. They are denoted as X. So let's move on. Type of regression analysis techniques. Types. So linear regression, this is a method used when the relationship between a variable is what? Linear. Meaning the change in dependent variable is proportional to the change in independent variable. So you can see that we're just talking about one dependent and one independent. We also have multiple regression. This model is for what? Simple linear regression, and is what is extended to the account for relationship between dependent variable y and p independent variables. So this is where we have one dependent variable but multiple what? Dependent independent variables. So you can see here where we are. I'm saying we have x1, we have x2 till we xp. Nth time we don't know how it's going to be. But multiple regression is different from linear regression. Linear regression is just leading you to do what? Just have one dependent and independent. But when you're talking about multiple regression, you're having what? One dependent and multiple what? Independent. So we also have logistic regression. When you talk about regression, this is used to predict categorical dependent variable such as yes or no, true or false, zero or one. It is used in classification tasks such as determining if a transaction is what? Fraudulent, or if an email is what? Is spam. Then aside logistic regression, we have ridge regression. So when you say ridge regression, we are talking about is a technique used to combat multicollinearity in linear regression models. So it adds to a penalty term to the regression equation to prevent what? Overfitting. It is more suitable when a data set contain more predictors variable than what? Than observation. Let's move on. We have lasso regression. This is like regression. Lasso regression also had a penalty term to the regression equation. However, lasso regression tends to shrinks some coefficient to zero, effectively performing variable selection. We also have polynomial regression, which is it uses polynomial functions to find the relationship between the dependent and independent variable. It can capture nonlinear regression relationship between variables, which may not be possible with simple linear regression. And we also have Bayesian linear regression. The Bayesian linear regression incorporates Bayesian statistics into linear regression framework. It allows for the estimation of parameters with uncertainty and the incorporation of what prior knowledge into the regression model. But in this class, the one looking at mainly is the what is the linear, where we are going to be looking at the OLS, which is the ordinary linear square. Now, let's move on. Simple linear regression, concept of best fit. Simple linear regression, concept of what? Best fit. So now, if you look at the definition, they said this line that minimizes the sum of squared residue between observed and what? Predicted values. We're going somewhere. Just work with me. So the equation, you have y equals to mx plus b. Somebody might see this equation and say, is this not an equation for gradient? We are just trying to make it look simplified. We're still going there where we get to see it's still more like the same thing. When you're trying to find the regression of something, just let's move on. So you see y to be the what? The dependent variable. You see x to be the what? The independent variable. Guess what? The dependent variable is your what? Outcome. The independent variable is your what? Your predictor. The dependent variable is your what? Your outcome. The independent variable is your what? Your predictor. So you have m to be the slope, y to be the intercept. Method, ordinary least square, OLS. And we also have some other methods too in terms of okay, likelihood, in terms of eye fitting, stuff like that as an example of the kind of method we can use to do what? Talk about linear do regression. So now let's move on. So visual representation, we talk about scatter plots with what? Data points. So the best fit line is drawn through the what? The point. So if you can see the examples and the first diagram we saw from when we started the class, you'll be able to get what I'm trying to say. Now, either a simple, we're talking about least square method now. Either a simple or multiple regression model is initially posed as a hypothesis concerning the relationship between dependent and independent variable. The least square method is the most widely used procedure for developing estimate of the model parameters. So for simple linear regression, the least square estimate the model parameters of B naught plus and B1. Just call it beta naught and beta 1. So I'm just calling it B. So we have parameters of beta naught and beta 1 are denoted as B naught and B1. So if you look at what I have here now, this is B naught plus B1x. This one are supposed to be in base. Sorry that it's like this. It's base. B naught plus B1. Those naught and 1 are bases. So X. So that's why I had to use, if you see now you have what? Y cap here. This Y cap is what? Equals to B naught plus what? B1x. So if I go back to this slide now, you can see why I use what? Y to be equals to what? Mx plus B, because the B1 is the one carrying X and the B naught is on its own. So we are representing this what? The least mean parameter are denoted. They are denoted this beta naught and beta 1 are denoted at B1 and B naught, naught and B1. So using this estimate, an estimated regression equation is constructed, which is known as what? Y cap equals to B naught plus what? B1x. So the graph of this estimated regression equation for simple linear regression is a straight line approximation of the relationship between what? Y and X. Y and X. So when we're talking about best fit, you should know why this is coming in. For example, let's look at this example. Let's look at this example. So the University Medical Center is conducting a study to examine the relationship between stress and blood pressure. Between stress and blood pressure. Now, they have collected data from 20 patients, including their stress test score and blood pressure reading. These data are represented in the scatter diagram. Yeah, we can see it here. With the stress scores on the horizontal axis. When we talk about horizontal, this is what we mean by horizontal, and the blood pressure values on the what? Vertical axis. Now, the line on the graph represents the estimated regression equation, which is what? Y cap equals to what? 42.3 plus what? 0.49x. 42 plus 3.3 plus what? 0.49x. So it's very easy for us to know that the parameter estimate for B naught is what? 42.3, and for B1 is what? 0.49. We are calculated using the least square method, and that calculation we'll get to do it. That's why I say when we get to see our assignment, we get to understand this thing, that even as our tools for analysis help us in terms of knowing present function. For example, for you to find a correlation in Excel, we use something called Corel, Correl, which helps you find a correlation. It should just ask you, give me the first variable you want to use, which is in one column. Give me the second one, which is another column, and help you find a correlation. Sharps. And when you want to do for regression too, yes, Excel, you can run it there. So any of the two we want to use, to perform our analysis can help us do this um, regression that we're trying to work on. So now you see that we were able to have what our model to be calculated to be this, where which were calculated using the what least square method. Now, from our findings, we find that a primary use of the estimated regression equation is to predict the value of the dependent variable. To do what? To predict the value of the what dependent variable when values for the independent variables are what? Are given. I've told us when you talk about dependent variables, it's denoted as what? Y. Independent is known as what? X. So for example, you can see this place. Obviously, we know that when we have a graph, the y is always vertical and the x is always what? Horizontal. So for example, now we're given a test score of what? 60 for stress. And we put it into our model. Our model was able to predict to us that we are going to have 71.7 as the blood pressure reading predicted. So if you see now this dot here is close to 71.1 because this is where 75 is. See it here. Let's say this is it. Because we are saying 60. So if you look at this now, we have been able to do what? Get this model. And how do we get the model? We add access to a particular data that we use. If we use our tools, we can just use those data. But if we are trying to solve them, you see we're going to get there. We're going to get there. So we're trying to solve them mathematically. You get to use some formulas to get your estimated values. When you have the B cap and the A cap. And why am I talking about B cap and A cap? I'm talking about the B naught and the B1. The B naught and the B1. Now, you could see that when they put this 60 here, which is what? Our independent variable, which is X, they're able to get to 71.7 as our what? So now we can literally see that as these values are what? Increasing, the blood pressure reading is what? It's also increasing. So the value predicted by the estimated regression equation are the points on the line in this particular figure you are seeing here. And the actual blood pressure reading are represented by the what? Points scattered about the line. So if you look at this kind of um regression now, you can see that in this place, this is what the correlation is clear. It's clear that it's going what? Positive. It's going what? Positive, because you can see that is as the stress test score is increasing, the blood pressure reading is doing what? It's increasing. So now, after we've done that, there's now something we need to understand too that we get to see most time. We call it R square. So when you have gotten, so for example now, if I use 50 and put it inside here, I'll be able to get the predicted y, right? If I put 60,
Excuse me,
I'll
sir.
okay.
I raised my hand.
Okay. Okay, what's your question? Sorry, I can't see the chat box. That's why I'm
Please,
always.
sir. I was thinking that, like, I got very excited when you talked about using Excel to do a correlation. And so I was hoping that you would open up an Excel file and then try doing the correlation for us. This is looking more theoretical. I have been observing that since the commencement of this statistical class. It's looking more theoretical, it's not being tailored towards some of these tools that we already know. And I think that's really where my own problem lies. Please, I don't know how you can help me out.
Okay, so I'll say that. Okay, so I'll say that the reason why this thing is being segmented into like sections for us to take is because if you could remember, if you know that there's a particular group for Excel to learn Excel, whereas they teach you about Excel and the rest. So why we talk about this theoretical thing is for you to understand what is going on behind this particular this particular functions when you use them in the tool. But as much as possible, I'll try to see how I can see if we can get a way to get the class to or a section to talk about what you just mentioned. So we'll see how we can do that. But literally we're supposed to look at this theoretical part, and as we're talking about this theoretical part aspect, diagrams are being shown to us to see how these things are working in terms of not you just seeing it and you use it and you are seeing something. What can you do when you use this thing, and how can you interpret them? How can you make it work? How can you understand what you are doing when you do these things? And like I said, That's why we are having this to be in sections. So for Excel, we have Excel, and when they were teaching Excel, it's possible, which I feel that they will have told you about, some functions in Excel and how you get to use this function in Excel. So, like I said, while I was explaining, I gave you an example of, when we're finding correlation, we do what? We use a particular function called Corel, which I spelled out. So if try make a little research on it, you'll be able to see that you just need the tables you want to work with, the columns. Okay, which ones do you want to find a correlation? Do you want to find a correlation between this table and this table? It will ask you, you know, how to highlight the first table you need, put a comma, second table you need for correlation. But we're talking about regression. So we also have ways we can find regression in terms of using a particular tool in tool in Excel too. But I'll see how I can we can see how we can work with that for you to start get probably apply this thing for it. So but then I'll get back to that while we are done with the class. So let's move on. Thank you. So it's noted. So now when we talk about this estimated value we have now gotten now, we will now see that we have been able to use these actual values that we have and put them into the model to get a predicted y. Now, but moving on, we now call something that the difference between the observed value of y and the value of y predicted by the estimated regression equation is called a residual. Now, sometimes when you perform regression analysis, you will see something called R square, and you're like, what's this thing talking about? What's this thing doing? Now, we call it what? Residual. So why, for example, here now we pick 60. You have a table that has to do with x and y. Then after solving to get your model, you now put this x inside to give you a predicted y, which is this 71 point. So let's say the real y we had was like 70 72 or 73. So the difference between the 71 and 73 is what we are going to find, that is called what? Residual. So the least square method chooses the what? The parameter estimate. The parameter estimate. Sorry, let me add. The parameter estimate. The parameter estimate that thought somebody was trying to. So the parameter estimate that such that the sum of the square residual is what? Is minimized. Let's move on. Assessing model fit, which is the R square. Assessing model fit, which is the what? R square. Now, when we talk about model fit, we're saying that, for example, his definition is the proportion of variance in the dependent variable explained by the what? The independent variable. The proportion of variance in the dependent variable explained by the what? The independent variable. We have the formula here, which is what? R square equals to 1 minus the sum of the square residual. What is residual? Residual is the differences between the observed value of and the what? Predicted value all over the total sum of what? Of squares. It ranges from 0 to 1. And what's the interpretation? It's what? It's explain when you have r squared to be equals 0, the model explain none of the variability in the data. When you have r squared to be equals to 1, the model explain all the variability in the data. So for example, when you have r squared to be equals to 0.75, the model explain that 75% of this variability in the data that the model is talking about, that is 75% of the variability in the data. So caution, IR squared doesn't always mean it's a good fit, because sometimes we need to consider what? Overfitting. Now we're going somewhere. Let's move. Analysis of variance and goodness of fit. So your R square, actually the main function is trying to do is to help you, tell you that okay, this thing you have done, does it fit? Is there a kind of big is there a kind of relationship between it, in between those dependent and independent variables you used? So using R square now, you say whose values lie between 0 and 1 provide a measure of goodness of fit. If the values are closer to 1, implies a better fit. That is, okay, there's a good fit between these two variables. And the values of R square equals 0 implies that there's no linear relationship between the dependent and the independent variables. That's to give you a confirmation that okay, yes, these things are not fit. So for the stress level research study that we just talked about now, that university study that we just said, so the value of the R square is what? 0.583, which is obviously in percentage as what? 58.3%. 58.3% of the total sum of the what? The square. And it can be explained by the what? The estimated regression equation, which is telling us the y cap equals to what? 42.3 plus 0.49x, which is our what equation, which is our regression in what equation. So we're able to find that the SO, and if this is telling us 58.3, you will see that it's more like a moderate fitness, telling us that okay, yeah, in terms of the variance, the variability, yeah, it's 58.3, and it's this moderate, moderately, the goodness of it is moderate, that kind of thing. So that's what our square is telling, is trying to help us do. Now, moving on, multiple regression basics. We want to talk about multiple regression, and if you could remember, I said we talk about popular one, which is what the linear, which is quite popular, where we use the OLS, which is the ordinary least square. But when we talk about multiple regression, we're talking about when you have a dependent variable with multiple independent variables, and the examples are going to be here. The examples are going to be here. So when you're talking about the definition of multiple regression, you're saying that it's using more than one independent variable to predict the dependent variable. So, for example, you use one independent variable and you're saying, this thing is not really looking like it's correct. Let's see if we can add another thing that would try to give us a very, very clear insight of our analysis of our prediction. So in this case, when we talk about y, we say it's the dependent variable x1, x2, xn, whatever, how long it is, an independent variable. Y, that's the b naught, which is known as what? Intercept. B1, B2, Bn is the regression coefficient. So what's the advantage? It can model complex relationship. It often provide better prediction than simple linear regression. An example of that is, okay, for example, you're trying to predict house pricing. You're trying to predict house pricing. So your dependent variable there now is your what? Is your house pricing, the prices. Now, what are going to be standing as your independent is, the square footage of the house, the number of bedroom, the location, the age of the house. So these are things that will help us determine that, the prices should be actually forecasted as, should be we should get to see this price to be at this particular, place, because of all these things that I've added as an additional thing to what, to give me a very quite clear prediction on what I want to do for this regression model. So when you're trying to interpret, so now if you look at this now with coefficient interpretation with what I just give the example. So you see house price equals what? 100,000, okay, plus the square feet, which is 50, plus 10,000 bedrooms minus what? 1,000, which is the age. So the interpretation is telling us that $50 increase in price per square feet, 10,000 increase per additional bedroom, and 1,000 decrease per year of age. So if the year of age is this, we're going to have it to be what? This price to be decreased. If you're having an increase in addition, you're trying to add a bedroom to it, 10,000. If you're trying to increase the price, this is what the interpretation of this particular model is giving us. And like I've said, the R square, this is telling us to, to help us, prevent overfitting in the model, and also tell us to see if it is good. So this R square in this place is actually very good, because it's be able to help you know whether you need to remove some independent coefficient you are variables you are adding, in order for you to prevent overfitting, and to know how you can get to say, okay, I think with this prediction I have make, I've been able to do what? Get to see what I am looking for in order for me to predict the house price. And the formula for this overfitting is down here, which is 1 minus open bracket 1 minus r square close bracket all open bracket n minus 1 close bracket over n minus k minus 1 close bracket. N is the number of observation, k is the what? Number of predictor. Or let's look at real world applications and case studies. Real world application and case studies. So for example, you're looking at the business example here, which is the sales prediction. You're trying to predict the monthly sales for a retail company. Your dependent variable is the monthly sale revenue that you have on a particular column. Independent variable, the advertising spend, how much they spend on and advertising, the economic indicator like the consumer confidence index, the seasonality represented by what? Months or quarters. And when you have this as your independent variables, then your potential finding is you finding a positive correlation between the advertising spend and the sales. Oh, literally. So we're trying to say, because we spent more on advertisement, we're able to get more sales. Seasonal peaks during holiday months. Impact of economic indicators on purchasing behaviors. Oh, what if this particular way of this economy is the one, that kind of thing. So the application, this is you trying to optimize advertising budget and inventory what? Management, based on what? Using regression analysis to do what? To predict the model. You're using to predict the sales to predict for a monthly sale for a retail company. Another example of a real world application, you're talking about healthcare example. So a patient recovery time. You're trying to estimate hospital stay duration for surgical patient. The dependent variable is the length of hospital stay. So this person has stayed in this hospital for a while. So we have a column having that length of hospital stay in days. The independent variable, we are talking about the age of the patient, the severity of the condition measured on scale, type of surgery that they did, the pre-existing health conditions. Now, when you try to find this thing, you can get to find potential findings. Say there's a positive correlation between the age and the hospital stay. Oh, because this person is quite older, and as per that's why this person is staying longer in this hospital. Oh, as a young person, you just want to quickly, you have stuff to, that kind of thing. Regression is helping you do that prediction for the patient recovery time. That's what you're trying to find out. Certain type of surgery associated with longer recovery time. So, oh, because we perform this kind of surgery with this person, you using the dependent variable and the dependent variable is getting to tell you that, oh, probably that's why this person is staying longer. So what is the application? It's trying to improve the resource allocation and the patient care planning. Regression is helping us do that based on how we've been able to do what? Use this dependent and independent variable to do what? To predict. And the last one I want to talk about is the environmental science example. So climate change. So you're trying to analyze factors influencing global temperature changes. The dependent variables is global average temperature anomaly. Then independent, you're talking about atmospheric CO2 levels, solar activities, volcanic eruption measured by aerosol optical depths, El Nino La and El Nino and La Nina cycles. So when you have this as your independent variables now, and try to use them as, because obviously their values are going to be in the column. Then finding this, they are finding potential findings. You are saying, oh, there's a strong correlation between the CO2 levels and temperatures. Well, probably because there's an increase in CO2 level, the temperature is increasing. Impact of major volcanic eruption on short time cooling. Influence of solar cycles on the what? Temperatures variation. So regression helps us, find these things, which helps us in terms of application, improve the climate model and inform policy decisions based on the fact that we know that we have these independent variables. You know that this is the dependent variable. This is what we're trying to do. So these are the examples and the real life applications that we can see that regression is helping us, to that can help us. It can help us do in order for us to get insight and know what to do next. Conclusion: correlation and regression are powerful tools for understanding relationship in data. Key takeaways: correlation measures relations strength and what? This them direction. Simple linear regression models relation between two variables. Multiple regression though extend to more complex scenarios. Actually, real-world applications span various fields. So always remember to interpret results in context and be conscious of over-interpreting correlations. That's what sometimes multiple regression can help us do. And that will be bring an end to the what? To the class that we're having. It's an end to the class we're having. Now let's look at our assignment. Let's look at our assignment. Let's look at our assignment. Now, our assignment is saying what? Given the data. So this one I want us to do it theoretically. Theoretically, because yeah, with the function here, we can help us do this, but I want us to do so. We have this particular data, and you can see I've been able to give you that. Okay, this is what we mean by our what? Our model. This is the model here. And if you can remember, the one having bx is what? B1x plus a. This a is your b naught. Don't forget. So it can be anyhow you want to arrange it. You see that I have b naught plus what? B1x. So now, how do you find b? N summation xy. You can see in this particular question here, you have x and y. These are the values. N summation n is what? The number of values. What do we have? 1, 2, 3, 4, 5. Yes, that's what n is. N is 5. Constant. Summation xy, which is multiplication of both of them, minus summation x, sum of x, times summation then summation y. You multiply them. You have to find a different the summation x, summation y. Then you subtract from the summation of the multiplication of x and y all over n x squared. This x, the summation. You find x. You do another table, square this x, and get the summation minus summation of x in square. That's it. The summation of x, then square it will give you what b is. Then to find a will be the mean of y, which is this y. You find the mean of y minus, after getting the value of b, times the mean of x. The value of b times mean of x is now what you find as a, which is y bar minus b times x bar will give you what? A. Then with that, you'll be able to get your what? Your regression. Now with this, now when you put in a particular value here of x, we'll be telling you, we'll give you a predicted value of what you have. So for example, compare it. Is it going to be 8 or a particular value? So aside that, let's say she find what correlation too. If you go to the front of the slide, you see the correlation formula, which is using the same data set that we have here. Then for you to find R squared, don't forget it's the difference between your what observed value and what the predicted value, which is where you whatever you get there, you now do what you square it, get the summation, whatever you get, you'll be able to get what be able to tell us what and with the formula I've given the formula in the slide to tell us whether there's a goodness or fit for the data that is here. And that's that of our assignment. I want us to do it what? Theoretically, so which is literally going to help us have the information well understood. Thank you. And that's the end of the class. Now, I'll take questions. I'll take questions. I'll take
So I
questions.
have a question.